Okay, welcome back everyone. In this example from chapter 10, we're going to be looking at rotational dynamics and statics. And basically what we have is a drum which is attached by its center to a rod which attaches to a wall. It's in contact with the wall at one point, and there's friction between the cylinder and the wall. And we're given a bunch of information about it: the mass, the radius, and the moment of inertia. And we're asked to find the force of support from the rod, which is at an angle of 30 degrees. Then we're asked to find the angular acceleration. And let's first draw in forces. We're given a tension downwards of 60 newtons. We know that there's going to be gravity, mg, acting at the center of mass. The force of the rod actually acts up and to the left, and we can decompose that in a moment. And then our last force is going to be friction. And so we have to think about the relative motion here. So the relative motion is that the cylinder is going to be rotating kind of this way in a clockwise sense, and so that means that the wall will resist that, or friction will go downwards, and that's going to be kinetic friction. So in order to calculate, and we also have a normal force. Okay, now how did I know that we had to have a normal force? Well, the first thing is that the horizontal acceleration of the center of mass, so AX of the center of mass, was 0. And similarly, AY for the center of mass is 0. And so this leads to the fact that the net force in the x direction is 0, and the net force in the y direction is 0. So let's set those up first. In the x direction, all we have is the x component of the force from the rod. So what we could say is that the normal force, which goes, let's say that to the right and up are our positive directions. The normal force goes to the right, so it's positive. The force of the rod is going to the left, but we actually need Fr sine 30 degrees. And that has to add up to give us 0. Next, we can write the net force in the y direction must also equal to 0. And so this means that the only positive force is going to be Fr cosine of 30 degrees. Everything else, kinetic friction, the weight of the drum, and the tension, are all negative. Okay, now this looks a bit clunky, but we can actually solve this system and find Fr from that. So the way that I'm going to do that is note from my first equation that the normal force is equal to 1/2 Fr sine of 30. Then in my second equation, I can write Fr root 3 over 2 cosine of 30 minus Fk. And if you remember, friction, kinetic friction, is mu k times F normal. So that's minus mu k. Well, hold on a second. Mu k is 1/4, and the normal force is 1/2 Fr. Okay, then we have minus mg, and m is 16, g is 9.8, and t is 60, so that's equal to 0. So I could say that Fr times root 3 over 2 minus 1/8 is equal to 60 plus 16 times 9.8. And so this gives me Fr is equal to about 293 newtons. So the support force from the rod is 293. Okay, so that does it for part A. Part B, we're trying to find the angular acceleration of the rod. And to do this, we have to examine torques. Now we don't have statics. What we have is that the net torque is equal to I times alpha. And so this is Newton's second law for rotation. Instead of net force, we have torque. Instead of mass, we have moment of inertia. And instead of acceleration, we have angular acceleration. And so I'll just redraw the drum right here. The only forces that are going to cause torques are tension and friction. And we can actually calculate friction now because first of all we know friction is equal to mu k times the normal force, but we know that the normal force is 1/2 of Fr. So that means that the normal force is going to be approximately 146 newtons, and Fk will be 1/4 of that. And so friction will be about 36.6 newtons. And so what this tells us is that if friction is 36.6 and tension is 60, well, tension's going to win and we're going to accelerate in the clockwise direction. Okay, and so we might as well make that our positive direction for torques. Normally that's not what we do. Normally we say that counterclockwise torques are positive, but in this case we'll do the opposite. And so the net torque is going to be the torque caused by the tension plus the torque caused by friction, and that's going to be equal to I times alpha. And the torque caused by tension is going to be simply the force of tension times the radius, and we're given a radius of newtons and meters, so 18 centimeters is 0.180 meters, okay, because we have to think about the lever arm. And just a reminder that torque is actually R cross F, which is magnitude of R, magnitude of F, times the sine of the angle between them. So if you recall, this is an example of the vector cross product. Okay, but when R is perpendicular to F, we can just write that torque is equal to F times R. So that's what's going on here, force times radius. Okay, then we have to subtract the torque caused by friction, 36.6 newtons, times the same radius. It also acts at a radius of R, and that's going to be equal to, running out of space, I'll do a new line, the moment of inertia times alpha. Okay, and let's see what this gives us. Oh, sorry, it's kilogram meter squared. Okay, so that gives us alpha of about 16.2 radians per second squared. And my units should be okay for this. Okay, so there's an example of how to apply Newton's second law for rotation, torque, to a fairly complex problem.